Good afternoon or good evening, everyone. Thanks for having us. My name's Dave Beattie from Dash Engineering, and firstly, I'd like to thank Keenan from Bearing News and all the associated staff behind the Bearing News people for getting this forum ready and for us to be able to present to you guys what we hopefully you'll find interesting today. In a nutshell, Dash Engineering are impartial and independent bearing consultants. We specialise in bearing failure analysis. Our senior staff have backgrounds in NSK and SKF, as well as bearing distributor networks. So we have a fairly technical knowledge. From that knowledge, we've got some fairly broad industry exposure, as you can see there. And if we move on to the next slide for us, Al. What we do fundamentally within these industries is we do investigations on failed bearings. So you can see our small workshop there. We don't have a lot of high-tech equipment per se. We have young, smart engineers that have the ability to think and are able to pull bearings apart, look at the raceway surfaces and the defects that are occurred, and we then put those pieces back together again as to what the failure modes are. We have some technology in the way of microscopes and things like that, but that's fundamentally what we do. We get our hands dirty, we pull things apart, we work with our customers and work out what the root causes are of these failure modes. So if we move on to the next slide, Al. So again, you can see there our benches, very simple. We line them up, we pull things apart, we gather an understanding of what's actually happened, we ensure that we understand what's happened, we share that with the customer, and then from that, we are able to work with our customers to provide them with an engineered solution. And that's what Alan's going to talk about today. So if we go on to the next slide, Al, you can see this is one that's just come into our office in the last couple of days. It's a bearing from it's a spherical roller bearing from a conveyor pulley, and you can see the extreme damage as a consequence of the contamination in there. So without stealing Alan's thunder any further, he's worked very closely with some of our key mining customers, and we've improved the reliability of their rolling element bearings, especially spherical roller bearings in dirty applications, such that they don't have these issues anymore. And Alan's going to go into some great detail with that for you. So thank you for your time. Thank you for having us. And hopefully you get a lot of enjoyment from what Alan's going to present. And we are keen to answer any questions obviously after this, because hopefully it will generate a lot of questions that we can work with you on. Thanks a lot.
Thank you, Dave, and hello everybody, and thank you for taking the time to view this presentation. I certainly hope that you'll find it interesting. We certainly have found the whole process interesting, and I'd like to share our knowledge and our success, and see whether you guys will get some benefit from it. So what I'm going to talk about is a case study detailing Dash Engineering's investigation of conveyor pulley bearing failures. This process established the root cause and highlighted the ineffectiveness of current solutions on offer. And furthermore, it led us to the development of an engineered solution for this particular type of failure. When I say conveyor pulley bearing failures, this is an indication of the sort of conveyor pulley that we're dealing with. This is a picture of a 2-meter diameter conveyor pulley. This is a high tension bend pulley running off of a drive station in Western Australia's Pilbara region, which is renowned for one of the world's largest iron ore reserves. This particular conveyor system is 27 kilometres long. It conveys approximately 30 million tonnes of iron ore per annum. And in some cases, in some pulley locations of this particular size of pulley, their mean time between failure is around 6 months, which is a little disappointing for our clients because the expected life is something around 8 years. So a little bit of background, as David mentioned before, Dash Engineering's core business is failure analysis of machine components, predominantly bearings. And in Dash Engineering's lifetime, we have completed in excess of 300 conveyor pulley bearing failure investigations. The overwhelming majority of these failures can be attributed to contamination in the form of dirt and water. In other words, conveyed material and water ingress to the bearing housing and the bearing itself. To give you an indication of the typical bearing failures that we witness, there's things such as this. This is a typical, this is where the bearing housing cap has been lifted during the rebuild of the pulley, and this is the sort of thing we encounter. Again, there's an example of a bearing that has catastrophically failed, effectively dismantled itself during operation. And again, a bearing, there's a common theme with everything, all of these conveyor pulley bearings that we see upon strip down of the pulley, and that is, as you can see, a combination of grease mixed with conveyed material and water. Water being the predominant killer of the bearings. We quite often see, that's a perfect example of what we quite often see, a lot of water in the housing mixed with the grease, mixed with the abrasive contaminant of the conveyed material, making its way into the bearing housing and obviously the bearing. This is another example of what we see where the bearing is intact. To all intents and purposes, it hasn't failed, and yet it's completely full of what used to be grease, but now is a mixture of contamination and grease. And then when we get to the investigation part of it and we actually get the bearing removed from the shaft and back to our workshop, this is generally what we see. We see grease that is no longer grease. It's a combination of water and dirt. And in this case, you can see that the outer ring of the bearing is in fact fractured, and the bearing had failed catastrophically. When we actually get through our investigation and manage to clean the contaminated grease, we generally find something like this, where, and this is a picture of an outer ring of a large spherical roller bearing from a conveyor pulley, and you can see that the outer ring is badly spalled and also fractured. So we ask the question, why is it so? Why is it that these conveyor pulley bearings become so badly contaminated in a relatively short period of time? Well, what we need to do, firstly, is have a look at what is the standard currently for sealing conveyor pulley bearing housings. Taconite seals are termed taconite seals. Taconite is actually a very, very fine form of iron ore. Taconite seals were developed in the USA in the 60s, so 60 plus years ago now. So were developed to try and seal out taconite dust. Taconite is effectively moon dust. It's the sort of thing that when you're walking through a mine site and you put your foot down, a big plume of dust comes up. That is taconite. It's very fine, very abrasive, and obviously very difficult to seal out of a bearing housing. Today, there are a number of different versions of these seals, but the fundamental design remains the same. They are a grease-filled labyrinth in combination with a contact lip seal. If we have a look at the various different types that are available today, we can see along the bottom of the page there, there's 5 different types. From left to right, the one on the far left can be considered the original or a standard taconite seal. So we can see that we have a labyrinth ring which rotates with the shaft, is driven by an O-ring on the shaft. It rotates relative to a static labyrinth carrier, which is attached to the housing. And then behind that, we have a contact lip seal, and in this case, it's a V-ring running on a wear face. You can see that the picture next to that to the right is a version of that. It's the modern day version, if you like, where the labyrinth runner, which is attached to the shaft, is just a molded rubber element. This, in fact, has 2 contact lip seals, one on the outside and one on the inside. Next to that, in the middle there, is a version of that. That is simply a different version of that from a different manufacturer. And then the 2 pictures, cross-section on pictures on the right-hand side there, you'll see that quite often used today is a vertical labyrinth. This is a development of the taconite seal where the labyrinth or the tortuous path is in a vertical arrangement, but again, it's in front of a contact lip seal. So fundamentally, the design is the same, or the function of the seals is the same. Furthermore, currently recommended by suppliers of bearing housings and bearings and bearing manufacturers is what has been coined by a major bearing manufacturer to be the 3-barrier solution. Now, the 3 barriers are firstly the number 1 barrier being grease, which is employed as a sealing medium within the labyrinth. So fundamentally, how the taconite seal was designed. The second barrier is a quantity of grease that is put into the bearing housing when it's assembled. And the excess grease within the housing cavity is there to act as an additional barrier, a second barrier. And then the third barrier in recent years has been the use of sealed spherical roller bearings. So integral seals on either side of the bearing is the third barrier. It begs the question to us at Dash Engineering that if a taconite seal works, then why do we require 2 further barriers? And why do we continually see this? Now, this is a good example of an investigation that we did on a conveyor pulley bearing that had utilised the 3-barrier system. So this had a taconite seal on the pulley side of the housing, it had a fully sealed spherical roller bearing, and it had excess grease in the housing, and yet it appears that the contamination has made it all the way through those 3 barriers and out of the blind side cap of the housing. This leads us on to a process that Dash Engineering coined as contamination migration. It is a process where contamination mixes with the grease in the labyrinth seal and utilises the shaft rotation to breach the contact seal, which is behind the labyrinth, and migrate to the bearing. The grease feed that is supposed to purge the labyrinth of any contamination actually accelerates the breaching of the contact seal, and the excess grease that is put into the housing cavity assists the migration of this contamination by acting as a pipeline. To put it in visual terms, contamination migration, this is a good example of it. This is a conveyor pulley bearing where the pulley has been sent to a rebuilder for rebuild, and we lifted the cap of the bearing housing, and we see this excess grease. Obviously, we have our taconite seal here next to the pulley, and then in between the bearing and that taconite seal, we have this excess grease in the housing, and you can see that it's a lot of barrier of grease, which appears to be reasonably okay. A little bit of contamination on the outside there, but we can also see that on the blind side of the housing, furthest away from the pulley, we can see this contaminated grease. Further investigation, when we managed to carefully cut through this stagnant grease between the taconite seal and the bearing, we can see when we peel it back that we have a layer of contamination, a layer of this brown combination of water, abrasive material, and grease. To give you a better look at it, once we've peeled that back, we can see this cross section here of effectively nice, clean blue grease, and then this pipeline of contamination which is running along the shaft. It has breached the contact seal behind the labyrinth seal in the taconite and made its way along the shaft to the bearing. And again, a clearer close-up picture, we can see a distinct line. We've got our stagnant, clean grease, which is acting as our supposed barrier to contamination. And then this distinct line of contamination. And you can see that the stagnant grease is acting as a pipeline for this contamination migration. Remembering that this is what we initially saw when we lifted the cap of the housing. So to the untrained eye, this would appear, yeah, okay, there's some contamination in there. It's got through the bearing. The bearing seems intact. Happy days. Things seem to have been functioning. But as I showed previously, it's not what we see that is necessarily the case. So as part of a pulley life enhancement project, which was commissioned by a major mining client of ours in the iron ore industry, Dash Engineering conducted field trials with bearing housings that didn't have the second barrier. So there was no excess grease in the housing cavity. And that enabled us to install endoscopic monitoring into the bearing housing so that we could actually see what was happening inside. And we also developed a workshop test rig, which ran in our workshop in order to simulate a variety of contamination conditions. To give you guys an example of some of these trials, firstly, a field trial. The example that I'm going to use here was a 2-metre high tension bend pulley, 2-metre diameter pulley. The exact pulley that I showed you a picture of at the start. It employs a 231/88 bearing, and many of you in the bearing industry will recognise the size of that, but it is in fact a 410mm shaft. So this is a sizable bearing and a sizable pulley. So what we did, as I said, we employed endoscopic monitoring. So we permanently installed endoscopes into the housing. So we drilled through the housing and installed endoscopes in the cavity between the taconite seal and the bearing. So what we're looking at there, just to orient the picture for you, is on the left-hand side here, we have a sealed spherical roller bearing. So where my pointer is there, you can see that is actually the side seal of the bearing. And then we have the inner ring of the bearing and the adapter sleeve, which attaches the bearing to the shaft. And then this illuminated part here is the cast iron cavity of the housing. And then this black void is the entry point of the seal to the housing. So effectively, if any contamination was to get into the housing, it would come through this entry point. And you can actually see there that there is a little bit of grease that has come through the taconite seal when the technicians initially charged the labyrinth with grease. So this photo was taken prior to the pulley commencing operation. This picture was taken 2 weeks after commencement of operation. So it's quite obvious that a substantial amount of grease and probably contamination has entered the bearing housing. 13 months later, the conveyor pulley was taken out in a standard scheduled shutdown, and we see by lifting the cap of the bearing housing, we can see that we have excess grease in the housing cavity, remembering that it was completely clear of grease to start with. So all of this grease has come from the taconite seal purging system. There's a significant amount of contamination with that grease, and we can see that we have a line of contamination migration along the shaft. When we pulled the bearing out of the housing, this picture was taken of the base of the housing. So this is the excess grease that came through the taconite seal, and we can see that we have this build-up of clean grease in the where the taconite seal spigots into the housing, and then there's a layer of contamination where this grease touched the shaft. So effectively, the contamination migration process has been proved perfectly in that once contamination breaches the seal, it uses shaft rotation to migrate along the shaft to the bearing. Another example is our test rig results, and our test rig was running 24 hours a day, 7 days a week, and it enabled us, as I said before, to simulate a number of different contamination conditions. Now, the picture that we see there, again, to orient what you're looking at, the shiny side on the right here is the lock nut from the adapter sleeve that's attaching the bearing to the shaft, and obviously we have the shaft here, and then we have a one of the latest labyrinth type taconite arrangements, where this is the molded rubber type element that spins with the shaft. Now you can see that the contaminated grease has just breached the seal and is just starting to make its way along the shaft. Now this is after 30 days of continual operation. After 10 more days, so 40 days in total operation, we can see that the contaminated grease is progressing quite substantially along the shaft, and then again another 10 subsequent days, so 50 days in total, and we can see that a substantial amount of contaminated grease is making its way towards the bearing. Now, it should be noted that the initial 30-day picture is only 10 days after contamination was introduced. We ran this particular test for 20 days with no contamination, and the seal didn't breach. But as soon as contamination was introduced, the seal breached. Now, our client, a major iron ore mining company, which transports or who conveys around 330 million tonnes of iron ore per annum, acknowledged that contamination migration process does in fact happen, and also conceded that there didn't appear to be a taconite seal solution that was effective. So at that point, Dash Engineering, we were encouraged to develop an engineered solution. And the solution that we developed, we have termed a SAPO seal, which you can see pictures of there. What we've got to keep in mind when we're trying to solve this problem is that conveyor pulleys are a misalignable application. And traditional taconite seals do not allow for misalignment. Now, when we say a misalignable application, these bearing housings contain spherical roller bearings. Spherical roller bearing is designed to allow or to accommodate misalignment. Conveyor pulleys need to accommodate misalignment. They are quite often adjusted for belt tracking. It's quite common that the machine bases that these conveyor pulley bearing housings are attached to are not necessarily accurate. Alignment of pulleys can be costly, time-consuming, cumbersome, and pulleys are then adjusted and then alignment is lost. So we can see that the spherical roller bearing accommodates misalignment, but then if we combine it with a taconite seal, that misalignment capability is lost. And in fact, manufacturers quote figures as low as 0.25 of a degree or 0.5 of a degree misalignment capability, when the bearing itself can accommodate up to 2.5 degrees in most cases. So if we are to develop a seal that accommodates misalignment, the challenge is that the alignment angle originates at the center point of the bearing. So you can see here we have a diagram of a bearing that is misaligned by 2.5 degrees. So the shaft is misaligned in relation to the bearing housing by 2.5 degrees. So the bearing has swiveled on its radius. But if we are to develop a seal that can cope with this misalignment, then it needs to swivel in a similar fashion to the bearing, but it also needs to move radially to accommodate this movement of the shaft, because it is moving at a radius that is the center point of the bearing. So the challenge is to develop a seal that functions as a seal, but it can also move in such a regard. The other thing to take into account is that a floating bearing on a conveyor pulley moves actually in the housing. So the seal must accommodate for such axial movement. And this is another failing or another shortcoming of the taconite seal design, in that quite often the labyrinth rings will not move on the shaft, and therefore the only movement that is allowable is the clearance that's in the labyrinth itself. So we need a seal that can swivel and articulate radially. So the SAPO seal was developed, and we're quite proud of it. SAPO is an acronym that stands for self-aligning pressurized oil. The system is maintainable, monitorable, and predictable. SAPO seals have an oil cavity, and that oil cavity enables the seal to be lubricated, because grease will not lubricate a contact lip seal. In order to have longevity of the sealing lips, oil is employed as a lubricant. The oil cavity allows us to monitor the condition of the seal itself. And we can also monitor any ingress of contamination to the seal. And all this can be done in real time without stopping the machine. The other thing it enables us to do is that should we sample oil from the seal and detect contamination ingress, we can in fact remove that contamination by changing the oil that's in the seal. This is the system that we have developed and has so far functioned extremely successfully. The other thing the system enables us to do, and this is the really exciting part for me, maybe because I'm a nerdy engineer, but I do like to be able to see what's going on inside a machine. So because the SAPO seal doesn't need the excess grease in the housing cavity, we can actually, on critical pulleys, install permanently installed endoscopes. And this is actually a video clip, which I'll play for you in a second, but just to so that you know what you're looking at. So effectively, this is an endoscopic picture of the inside of the housing cavity. This is a head pulley. So the housing is mounted vertically on the machine frame. So we are actually looking directly down at the housing split line, which is this line that you can see at the bottom of the housing here. So our bearing is here on the bottom right-hand side of the picture. So again, we're looking at, this is the bearing seal, this is the bearing in a ring, this is the adapter sleeve, which attaches the bearing to the shaft. This is the shaft, which is pointing up to the top left of the picture. And then, of course, this is our void that the SAPO seal is on the other side of. So anything that comes through the seal will come through this section here. So if we just play that video clip, you can see it's a sealed bearing. So we can see as the shaft rotates, we can see the grease that is starting to come out of the bearing seal as a result of the lubrication regime for the bearing. The other obvious advantage of this is we can not only monitor if contamination gets into the bearing housing, but we can monitor whether the grease rate is excessive to the bearing itself. So it's pretty cool. It's pretty cool. We actually get to see what's inside. So we've got multiple forms of monitoring with this SAPO seal system. So outcomes of the project. A good example is the very high tension bend pulley that I showed a picture of right at the start. We did our experiment or our trial with the taconite seal with a grease-free cavity. And you can see the picture on the left here is what happened after 13 months in service. We had our contamination migration, the taconite seal was breached, the excess grease filled the housing cavity, and effectively the bearing was very close to failure. After installing SAPO seals, and the pulley was in for almost exactly the same time, 13 months, and you can see that we have a clean housing cavity, a clean shaft, no discernible contamination entered the bearing housing. So in summary, we currently have 18 SAPO equipped pulleys operating in the Pilbara. The Pilbara, for our international viewers, is the iron ore mining area of Western Australia. And it's I believe, the largest iron ore producer globally. We have a further 14 SAPO equipped pulleys scheduled to be installed. And in some cases, the SAPO equipped pulleys have achieved 3 times mean time between failure and are still running. So that's 3 times plus. To date, no pulley has been removed as a result of a seal failure. So in summary, I'd like to thank you for taking the time to view this presentation. I'm sure you have plenty of questions. We're certainly very proud of the achievements of our engineered solution, and we'd certainly hope to assist anybody or any of you who think it may help. Thank you, and goodbye.
Thanks, guys.